All right, I just started recording. So hello, good morning, everybody, wherever you might be. It is my great pleasure to start the third installment of our graph algebra course. And yeah, I'm missing a part of my notes. I guess I'll have to improvise. I would like to start with a certain overview of the topic so that you have like a roadmap. I don't know about you, but if I travel somewhere, I always need to put my Google Maps on so that I know, where are traffic jams, which way should I go? Maybe I can choose an alternative route. For me, it's very difficult to act without any roadmap. So that's what I want to provide for you to begin with. And to this end, I will start sharing the screen, whiteboard, share. Okay, now all should be visible. I move my controls here. Participants can now see your whiteboard. That's exactly what I hoped for. Okay, can someone confirm? Can you see my whiteboard?
Yes, we can.
Okay, perfect. Sorry about these technicalities, but hybrid teaching is most demanding, and I want to make sure that nothing goes wrong. Okay, so the title of the lecture course is the basics of the K-theory eraser of graph algebras. So you see from the start that you have two ingredients in the very title. One is the K-theory, and here by the K-theory, I mean the K-theory of sister algebras. Now, this is a very important topic in mathematics. I dare say that this is exactly one of the key mainstreams in mathematics. When you would count the number of Fields medalists who contributed to K-theory, this is quite a number. And one of the most important theorems of the 20th century about periodicity is K-theory of sister algebras. It implies another super famous theorem, the Atiyah-Singer index theorem, for which these two guys got the Abel Prize, 800,000 euros. So that's really quite an important topic, and it's applicable at many places. K-theory as such was invented by Grothendieck to generalize the Riemann-Roch theorem. Then Atiyah and Hirzebruch took it to topology, to the usual topology as we study manifolds and so on in differential geometry. And then people realized that, well, we can just describe spaces in terms of sister algebras by the Gelfand-Eimer theorem. And then immediately we, instead of speaking of vector bundles, we speak about finite projective modules and everything rock and rolls. And then the K-theory turned out to be very important on its own sake. For instance, in topology, it allowed Adams to solve this vector fields on the sphere problem. In pure sister algebras, in operator algebras, in function analysis, this is absolutely key ingredient of famous Elliott's classification program of sister algebras. So just please take it for granted. This is really a mainstream of mathematics. On the other hand, you have graph algebras. Well, this is more of a niche topic, but not unimportant. And what I like about it is that it is at the intersection. It's something of algebra and analysis, and it's applicable in non-commutative topology. So graph algebras or graph sister algebras, that's the second ingredient and of this lecture course. And the goal is to combine the two. One of the key observations concerning the K-theory or graph sister algebras, maybe I'll add the C star so that you're not confused, is that graph sister algebras are sort of made for K-theory. Once you have your favorite sister algebra presented as a graph sister algebra, because that's quite a tricky thing. You might study your favorite sister algebra, and you might not know whether it is a graph sister algebra, and if it is, how to realize it as a graph sister algebra, how to find the graph for the sister algebra. These are very non-trivial theorems, very non-algebraic in nature. But once you make this transformation and you express your sister algebra as a graph sister algebra, then you can, by Rayburn-Szymański theorem, you can read off a K-theory from its graph. So these two things combine by this very powerful tool, which let me call effective calculations, can prove a lot and compute a lot. You can imply it in non-commissive topology. And what do I mean by the non-commissive topology? Just let me signal to you that based on the Gelfand-Naimark theorem, we know that if I take a unital commutative sister algebra, that this is necessarily the function sister algebra of all continuous complex valued functions on a compact house of topological space. So what we are doing, we are now viewing arbitrary sister algebras. When they are unital, we view them as function algebras on compact quantum spaces. And when the sister algebras are non-unital, then you simply have to replace C by C naught. So now you take functions vanishing at infinity on a locally compact house of space. And again, Gelfand-Naimark works. Every commutative sister algebra is of the form of being a function algebra of functions vanishing at infinity, continuous complex valued on a locally compact house of space. So to make this kind of Copernican transformation, we say that algebras are at the center of the universe and points are revolving around algebras, not as it was in the classical topology, that we have spaces made out of points and then we take algebras as secondary objects. So the idea of non-commissive topology and then non-commissive geometry based on non-commissive topology is exactly this Copernican transform, but algebras come first, points, if they exist, come later. So this way, you have these effective tools to study non-commutative sister algebras, and you view them as function algebras on some quantum spaces. But with the tools provided to you by these graph presentations, you can really say a lot, and you recover a lot of intuition that is lost when you go to the non-commissive setting. And now this classical intuition from algebraic topology is replaced by the intuition provided to you by graphs, which are very tangible objects. Okay, and now what I told you can be said about any course combining any course on the K-theory of graph algebras. That must be in any course. But I would like to tell you now what is particular about this lecture course, and it is that we study pullbacks of sister algebras. We focus on pullbacks of sister algebras. And we unravel them as pushouts, as coming from pushouts of graphs. Now, this unraveling of pullbacks of graph sister algebra as coming from pushouts of graphs, again, gives us some understanding that allows us to study quantum spaces. And we do it by applying the so-called Myovitorius principle. Now, what is the Myovitorius principle? Well, basically, it tells you that if you have a complicated space, you study it, you understand it by chopping it into pieces. You view, for instance, a sphere as the gluing of two disks over the boundary circle. So disks are much simpler than spheres, but you can go much further. For instance, you look at the complicated surface, for instance, real projective plane. That's a non-orientable compact surface. And it's actually quite hard to imagine it. But if you chop it into pieces, the picture is actually quite simple. So you take 3 squares, and then you glue 2 squares into a Mobius band, right? So it's like you are sleeping in the morning and you buckle up your belt and you do it incorrectly. This is the Mobius strip. And the advantage of the Mobius strip over the cylinder is that it has as the boundary just 1 circle, not 2 circles. And then you take the 3rd square, which you can view as a disk, and you glue to this boundary circle of a Mobius band this 3rd disk. And this is a real projective space. So you have the understanding of a very non-trivial, complicated surface with very interesting topology, non-orientable thing, as gluing something as simple as 3 squares. And this is the Myovitorius principle, to understand complicated spaces via their building blocks and gluing recipes. And that's what we can do here with pullbacks of sister algebras. Okay, formally speaking, you can say that once I have a pullback of sister algebras, it's already applying the Myovitorius principle. True, of course, technically, yes. But these are very abstract things, and we need some intuition that normally for commutative sister algebras we simply have from topology. And now when you go to operator algebras, to non-commutative operator algebras, this is gone. I mean, these are no longer functions and spaces. We call them quantum spaces, but how do we understand them? How do we manipulate on these quantum spaces? So here for graph sister algebras, we can have we can express the graph sister algebras in terms of their graphs, and what is very important for us, we can go much further. Under some assumptions, we can understand pullbacks of sister algebras as pushouts of graphs. And this is the new stuff. This is where we have this interaction. This is where we have new results. So if you want to join some research adventures and discover something and then publish it, then that's the area where I can help you with as a result of this course. Okay, because other stuff is well worked out, and of course you can always contribute in any area, but this is the tunnel at which we are digging. And what is now the main results that we are discussing? Well, I would call them push out to pullback theorems. I know that for the new of you who just joined the course this semester, it doesn't tell you much, but for people who attended my course in the previous semesters, at least the previous semester, that's clear what I mean by this. But I will explain in a second. Push out to pullback theorems. Well, what is a pushout? The pushout is a generalized recipe for gluing spaces. It's a little bit more than taking the set theoretical union of spaces, because you can contract part of the spaces before you do that. So for instance, you can obtain a two-sphere by gluing the unit disk with a point, and the gluing recipe is that you shrink the boundary circle of the disk, and then you also get the sphere. So pushout is a more general way of looking is a more general version of taking the set theoretical union. So the name of the game is first to see when, under which conditions, we can have pushouts of graphs, because in order to make sense of what you mean by a pushout, you must explain what you mean by a morphism. So some restrictions apply. You have to work it out, and that is what we are doing. So you find out for which graphs and for which morphisms we can have pushouts to begin with. Then we study for which morphisms and for which graphs we have a functor that transforms these morphisms of graphs into star homomorphisms of the graph sister algebras, so that we obtain a contravariant functor. That's not enough. We still have to verify that if I start with a pushout diagram of graphs, after applying this contravariant functor of assigning a graph sister algebra to a graph, I will get the pullback of sister algebras. And this requires a lot of works and a lot of conditions. And thus far, we have done it for path algebras in the previous semesters. In this semester, we want to do it for Kohn algebras and for Leavitt path algebras, and finally for graph sister algebras. So that's the plan for this semester. And this is very important, because only then when we make this identification, when we prove this pushout to pullback theorem, we can say, aha, this pushout of graphs is really the gluing of quantum spaces. Because remember, for us, quantum spaces are the abstract categorical duals of non-commutative sister algebras. Okay, if I am to have a geometric or topological interpretation of gluing of graphs, then they must have this property that the gluing of graphs will translate by this contravariant functor into the pullback of their respective sister algebras, graph sister algebras. Then I can say, aha, indeed, this gluing of graphs is actually gluing of quantum spaces. Okay. So this is what I gave you thus far is a kind of spatial orientation. I told you what the basic building blocks, ingredients of the course and how they are related to each other, how they interact. But now I'd like to give you more dynamical perspective, somehow something like the timeline. And let me label it as the hierarchy of concepts. So we start with something extremely elementary from the concept of a graph. Okay. Then once we have a graph, we can consider finite paths in graphs. And here in the first semester, the previous academic year, we made a very big detour into combinatorics of paths. Now, this has nothing to do with the program I just outlined for you, but it might be interesting more for people who do combinatorics or some, maybe computational topology, right? We have 2 PhD students who do computational topology, and one of them gave a talk in band level, and he was actually posing a very, very similar combinatorial problem in his talk as we did in the lecture. So that's Davide Gurnari, but this was a detour from my point of view. It's not needed for the picture outlined for you, but we spent many an hour studying combinatorics of paths, and this is quite fascinating in itself. It's really very, very nice piece of mathematics, but it's also very difficult because on one hand side you can very easily understand what you're talking about, but it's difficult to make any proofs, because you just have to do it with bare hands. You don't have many tools. All right, once we have paths, you can continue. And the next thing that you study are categories of graphs. You see, you should remember, right, that the category consists of a class of objects and the sets of morphisms between each pair of objects. So we have to specify what they are. The most plain category I can imagine is the category of sets. Objects are sets, and morphisms are maps. This is like the basic idea of what a category should be. But then, if you take all the sets and all maps, it's too much. Maybe you want to do just finite sets, and maybe you want to do just injective maps, or maybe only bijective, maybe only permutations. So you see, the name of the game is to specify what your category should be. I don't know if it's a true story, but I remember it from some historical movie that Michelangelo used to say. I mean, the sculpting is just removing redundant pieces of marble. The sculpture is inside. I just remove the redundant pieces of marble. So somehow, when you zoom into your category to be what you want it to be, you're like sculpting. Because if you take the ambient category, which is huge, okay, everything happens. This is like the universe, but it's an empty scene. And only when you have to remove these redundant pieces of marble to see the sculpture, to see what you want it to be. And when you consider graphs, this is especially important about morphisms. The issue of what morphisms should be to allow us to pull back theorems, that's quite a story. And we'll continue the story in this semester. And so this is, if you want, on the side of graphs, so that's combinatorial side. But now let me make this dividing line here and see what we have on the algebraic side. So for starters, of course, we have path algebras. And they are universal objects. They are very nice. I will show you definitions later on. So let me skip it right now. This is a very natural construction. To every graph, you can associate a path algebra. Which is very important. For instance, we discussed it a little bit, but we didn't dive into it. This is applied, for instance, in the study of the classification of finite dimensional algebras and representation theory. By the way, when you are in France, you have to be very careful with this abbreviation, because in France it means ferme dimanche, closed on Sundays. So when I was in Paris and I took some guide, I couldn't understand why the restaurant is finite dimensional. What do they mean by a finite dimensional restaurant? but this is given in English, so this is finite dimensional, not ferme dimanche. Okay, so that's we just signaled that there is such a thing. This is quite a story. There is a lot of mathematics going on over there. So path algebra is already very useful here. But that's not what we want to do from path algebras. And this is maybe before I say the step we want to take this semester, let me say what we did here. So here we studied really the pullbacks of path algebras. Pullbacks. Okay. So we had our first. Sorry. Here I forgot to write, but here we studied pushouts. So once we were sculpting in these categories to obtain categories in which we can do reasonable pushouts. Okay, and then we were doing it in such a way that we can cross the barrier and go from combinatorics to algebra and have these push-out to pullback theorems. Okay, so that's what was done in the previous 2 semesters. Okay, with I think the first semester ending somewhere here, and the second semester being over there. And now what we are going to do this semester. Well, already today, I want to define for you Kohn path algebras, to be more precise, relative Kohn path algebras, but the name is too long to write, so just let me write Kohn. Do not confuse it with Alan Kohn, the founder of non-commissive geometry. And then once we have a concept of Kohn algebras, I will finally, and again, already today, define for you Leavitt path algebras. And then, as promised in the syllabus of the course, I will define for you graph sister algebras as the universal developing sister algebras of Leavitt path algebras. Okay, so that's this graphy part. So we can ask, well, where is K-theory? Well, K-theory is somewhere here. And by the way, of course, we will study pullbacks in all these contexts. Okay. And again, this will be, because graphs are not changed. Everywhere there, whether it's a path algebra, Kohn path algebra, Leavitt path algebra, graph sister algebra, it always is associated to some underlying graph, okay? And we'll always be interested, this is the focal point of this lecture course, we'll always be interested in push-out to pullback results, okay? It's one of the reasons why this course is progressing so slowly, because we are not running it out of any book. I'm actually writing a book when teaching this course. So there is a number of results which are simply new. And when you do it like this, of course, you have to proceed slowly. So that's the price we pay for being a bit more original. Of course, I many say 70, 80%, I'm just using a textbook, but I think statistically like 20% was new stuff, which is not to be found in any book, except for the one we are writing. Okay, so here's K-theory. Here's K-theory. And on one hand side, even without any studies of pullbacks and without thinking of graph sister algebras coming from path algebras, you already have this remarkable theorem of Reborn and Szymański, which allows you to read off K groups of a graph sister algebra out of a graph. You shouldn't take it for granted that computing K groups is simple, and because it not always is simple, sometimes it's difficult, and it's even more difficult to establish generators of K groups, which is really the interesting question in most mathematical problems. So this theory of graph sister algebra allows you to do it. You have an incredible amount of tools. But in addition, we make something good even better, because here we can have a Myovitorius principle, okay? There is the Myovitorius 6-term exact sequence for surjective or one-surjective pullbacks of sister algebras in full generality, which is one of the key computational tools in K-theory. And time permitting, I'm going to prove to you this theorem in full generality. In the classical setting of topological spaces, this theorem was proven by Michael Atiyah, an idea by Atiyah. And then in the general setting of sister algebras, Paul Baum and myself, we generalized it to arbitrary sister algebras. I mean, the result is known. We just managed to get a proof which was exactly following Atiyah's footsteps. And it's always nice to follow a giant, because when these people do something, it's usually sometimes wrong. Don't misunderstand me, but so often they have such deep insight that it's advisable to see what they are doing and how they are doing. And this is what we did with Paul. We said, well, wait a second, this idea of the proof of Atiyah is so beautiful. Can we do it in the purely non-commissive setting? Yes, we can, in full generality. So I hope to show it to you. And on the other hand, we have this Rayburn-Szymański theorem that tells you, aha, if I have a graph, then the K groups of graph sister algebras such. They're given as kernels and co-kernels by maps between abelian groups. So, of course, you still have to compute it, but the difficulty of a computation is by several orders of magnitudes easier. Okay, and I think that's all what I wanted to tell you about how I view this lecture course, what already has happened and what I hope will happen. So now I can go into some more details and show you some slides. Because I apologize to Maciek, who attended my lectures about lectures in June, but he was the only one who attended it out of all of you. So now I'll stop sharing my whiteboard, and I will start sharing the screen. Yes. Okay, so I share the screen. Okay, this goes for later on, so I don't want it, so I kill it right now. Participants can see your screen. Okay, it's good. I have nothing embarrassing here. I just close this one, and oops. Okay, maybe I will just, because there's this nice application, which unfortunately I just closed. Okay, maybe I'll just start. Yes, okay. You see, this is a very, very cool application, but I want to open another file. So I don't want to kill the application. I just want to open another file. How do I do it? Oh, maybe I kill it here. Discard changes. Yes, and now open file from device. How about this? Yes, yes. Okay, and here are my slides. And you see the beauty of this is called drawboard PDF. And the beauty is that you can write on your slides. You can write on with a pen. So let me try it. I first have to start the pen. Yes, it works. And I can easily erase it. Wow. Good. So now that we have a technology, let me give you some more details about this lecture course. So that's something which I gave in Polish on 14th of June, if I remember correctly, as in the series of lectures about lectures. So sorry, Maciek, it's going to be the same stuff, but for everybody else, it's going to be new. And I will show you some details. So first, prerequisites. What I would like you to be familiar with are projective modules, exact sequences, Banach algebras and sister algebras, oriented graphs or quivers, and path algebras. So please don't panic, because the first three ingredients are absolutely standard. There are zillions of textbooks from which you can learn it. And my idea is that we will study it on the run, on the go at recitation classes. Yeah, so that's something I'm not writing a book about. This is absolutely standard bread and butter of mathematics. So I'm not going to write about it, but we will explore it during recitation classes. So you guys will teach each other about it, okay? But when it comes to oriented graphs and path algebras, well, that's of course far more niche. And I expect it as a prerequisite because this is what we studied in the previous semester. I cannot repeat 2 previous semesters. So oriented graphs was first semester, path algebras was the second semester. But this is combinatorics. So although you can spend hours and hours proving very difficult theorems, the very definitions are immediate. I made an experiment when I was teaching a graph algebra course at the University of Colorado at Boulder. And I asked my 15-year-old daughter to give a lecture instead of me, and she did it. So I could teach a 15-year-old high school student to give a full university lecture about graphs. And so this is a proof that this is conceptually very, very easy. Yeah? Everybody can grasp the definitions and work with them. The name of the game is to prove difficult and non-trivial things with this concept. The very concepts are extremely easy. And taking the book in writing and taking our YouTube channel, you can very quickly get yourself started and familiar with these two concepts, okay? And just understanding of these two concepts is enough to follow what I'm going to teach you during this semester, okay? But what we will study from scratch, starting today, Leavitt path algebras, then graph sister algebras. And then I'm a bit skeptical. I had to put it into the syllabus, but I don't know how much I'm going to do. Let's see. We have more lectures. This year, we're not losing any lectures. We have 15 lectures. Because I think in the previous semester, we had like 12 lectures or something because we had national holidays, whatnots, right? This time we have full 15 lectures for this lecture course. So I'll do my best to show you some foundations of the theory of operator algebras. I would like to prove for you there's Myovitorius 6-element exact sequence because Attia's proof is so beautiful and we took it to the full generality of sister algebras. And then examples from an application on non-commissive topology. Well, that's something which is always good to have, but if we skip it, there will be no tragedy. This is just to justify what we are doing and to have fun. So we will try to have as much fun as possible, but this is like the cherry on the cake. If there is no cherry on the cake, still you can eat the cake. Now, more precisely, what is in the syllabus? We will do the famous Kunz-Krieger relations, which turn a path algebra into a Leavitt path algebra and then into the graph sister algebra. And one of the things I want to insist on, I want to introduce graph sister algebras as the universal enveloping sister algebras of Leavitt path algebras. That's not the usual way. That's not the way Kunz and Krieger or Reber and Szymański were doing this. So this is the result of this enormous amount of new mathematics that happened starting 2004, where people realized that there is a fundamental link between path algebras and graph sister algebras. And then this area of Leavitt path algebras was developed, including K-theory issues and so on and so forth. So this is a very hot, although somewhat niche subject. And then, as I promised to you, we'll study pullbacks of graph sister algebras. Okay, so this is from the point of view of graph algebras, and from the point of view of K-theory. Well, I want to explain to you the usual standard 6-element short exact sequence of sister algebras. And then I want to do the 6-element Myovitorius exact sequence for one-surjective pullbacks of sister algebras. Oops, I'm sorry, I'm missing AS here. I was translating it from Polish to English, and here I skipped AS. Oh, but I have a pen, look. So that's why I'm using this. By the way, you can also correct me because I think you have a permission to write on my screen. So that's actually very funny when you have a seminar, somebody is speaking and somebody else correcting from the audience. It's possible. Of course, you can block it, but I think it's fun to have it within reason, of course. And then, as I told you, is Reber and Szymański theorem computing the K groups of graph sister algebras from their graphs. So that's what I'd like us to do. And finally, the cherry on the cake, the non-commissive topology. So the studies of, for instance, quantum balls, spheres, and projective spaces, both real and complex. And as I told you earlier, I want to, by proving these push-out to pullbacks theorems, I want to study the gluings of quantum spaces as gluings of graphs. Because gluings of quantum spaces is just, it doesn't have mathematical meaning. This is just a term, an idea. But gluing of graphs, that's a mathematical concept. So we are taking some ideas which motivates our work, but now we want to make it rigorous and prove some theorems. So then we have to explain them as gluings of graphs. Okay, now let's have some examples. So these are the Hong-Szymański quantum balls. Yeah, I know I didn't show you the definition of a graph yet. I will do it in a second, just for the sake of notation. But if I can do a definition by example, here's a graph. So you have a set of vertices and you have a set of edges, oriented edges, arrows. So the arrows have beginning and an end. And well, if you have a ball, how about having the boundary sphere of the ball? So you see in classical topology, the boundary sphere is a subset of a ball. The same is here with a graph. If you remove this last vertex and remove all arrows that end with this vertex, you'll get precisely the graph of a Waxman-Soyberman quantum sphere. Okay. And once you have a sphere, you know, and these are odd dimensional spheres, right? You have 2n-1. These are only odd dimensional spheres. You can also get even ones as pullbacks, but that's a different story. But whenever you have an odd dimensional sphere, then the equation is written using only complex variables, right? So I have z1 absolute value squared plus ... zn absolute value squared equal to 1. That's the equation of the sphere, which is 2n-1 dimension, right? But then, of course, you can act on points of the sphere by the unit circle. Let me note that's the unitary group U1, okay? So basically what you are doing, you take a point on the sphere, you take the coordinates zi, and you act by lambda simply by multiplying each of the zi by lambda. But lambda is a unitary complex number, so of course it doesn't change the equation. So this is the so-called diagonal action of a circle on the sphere. By the way, all graph sister algebras enjoy the circle action on graph sister algebras, which is usually actually a free action. So you have a nice quantum principle bundle as a result. But that's for the later on. That's the fun part, cherry on the cake. And you see, so once you have an action of a group on the space, you can take the quotient. And as you probably remember from high school, when you divide the odd dimensional sphere by the action of a circle, what do you get? Complex projective space, okay? And indeed, this is what happens here. On this graph sister algebra, I have the Yuan action, which is exactly, if you want, the quantization of a diagonal Yuan action on the odd dimensional sphere. And then you obtain the following graph, or the following graph sister algebra. Technically speaking, what you get, you get all elements in this sister algebra that are invariant under this action, okay? Because look, if you have a quotient space in classical topology, so say you take a space and you take the space of orbits by the action of a group. So how can you imagine the algebra of functions in the space of orbits? So these are all functions on the space which are constants on orbits, okay? So that's why when you have a quotient construction, you explain it in terms of sister algebras as a subalgebra construction. So I'm taking only the subalgebra of all these elements in my sister algebra, but they're invariant under the action of the circle. So this is like saying, I have all functions on my 2n-1 dimensional sphere, which are invariant under the circle action. And with this definition, you get another sister algebra, but lo and behold, you can express it again in terms of a graph. But this is a different graph. This graph is acyclic. It no longer has any loops, but it's at the expense of being now infinite. So between every vertex, okay, let me put it this way. Vertices are ordered from V0 to Vn, and between every vertex with a lower index and a vertex with a higher index, from this vertex with a lower index to the vertex with a higher index, you have countably infinitely many arrows. Okay, so that's the graph that you have. And I know that this is not rigorous mathematics, but I cannot resist telling you this intuition. So somehow what happens here is, yes, here you have only finitely many arrows between vertices, okay? But you have infinitely many paths, because I can go from V0 to V1 by just walking this arrow. But I can also wind around the circle and then walk this arrow. And I can wind around the circle a million times and go along this arrow, and so on and so forth. So at the end of the day, if you would count paths rather than arrows, you would see that from a vertex with a lower index to a vertex with a higher index, you can always go by infinitely many different paths. And that's somehow the idea which you have over here. This is such a graph, okay? Okay, and now, and rigorously you can say, aha, so this is by definition the sister algebra on this quantum Waxman-Soibelman sphere, but you take the fixed point under the U1 action, okay? Now, bibliography and YouTube. So first in the archive, there are lecture notes from my lecture in Colorado. It's called Graph Algebras. You can just Google my name or the name of my then PhD student, Mariusz Tobolski. Now he graduated, summa cum laude, so he's no longer a student. And he helped me to write the book for this lecture course. So that's like a compliment. I mean, the book I'm writing when teaching you stems out of this thing in the archive. Next, there is this book, Leavitt Path Algebras. This is this Springer lecture notes, the yellow book, okay? I strongly recommend it. This is a very good book. It's not thick, because there are some books, for instance, about path algebras themselves, which are just extremely thick. I mean, if somebody throws at you a book which is 600 pages long, it's kind of daunting. So this book is not daunting, and it's pretty nicely written. So for me, this is the basic reference for the course. So if we don't invent something ourselves, then we take it from this book. Okay? And it's Springer, so you can easily get it. Then if you want to understand K-theory, there is a beautiful book by Vegge Olsen. I think he's Danish. And it's a friendly approach to the K-theory of sister algebras. Indeed, this book is a very friendly approach to the K-theory of sister algebras, but it's a long book. It's a long book, but then it's really like written for high school children. So that's kind of funny because this is a very difficult topic and complicated, but this adjective friendly approach is not a lie. This is true. It's not just an advertising gimmick. Now, when you want to look at it at some algebraic backbones of what we're talking about, then a book which does, algebra representation theory, but from the point of view of graphs and paths, and then it's this book, Algebra Representation Theory by Erdmann and Thorsten Holm. Karin Edmund and Thorsten Holm. And finally, this is one of my most favorite books for sister algebras. It's by Gerard Murphy, a very nice Irish guy. I had the honor and pleasure of knowing him personally. And this book is remarkable because, again, it's not very long. It's pretty succinct, but it has all the basic stuff provided in a palatable manner. It's one, of course, you can have, I don't know, Cadison ring rows, and then you have 3 volumes, 300 pages each. I mean, this is a huge subject, right? And if you want to understand sister algebras in the spirit, I mean, all technicalities, this is not a book on non-commissive topology, but it gives you all technicalities that you need in non-commissive topology, okay? Which might be different from other needs. I mean, there are people who study just operators, not operator algebras. What will happen if I iterate the application of an operator in a Hilbert space? This is a completely different story. And now we have our YouTube channel. Please subscribe. Please subscribe. We have basically all lectures from the first semester and definitely all lectures from the second semester. You see, in the first semester, every now and then I would forget to push this record button. Then I got used to it, and all the lectures from the second semester are recorded. And you can ask, well, wait a second, how do I find? Of course, you can always Google it up. But we are going to have so-called Moodle Page. So again, people from the University of Warsaw, or people who attended the course before, know what I'm talking about. This is a special site to which you will have access. And over there, we store all course materials. So updated lecture notes, as I'm writing them for you, are over there. List of exercises to be done for recitation classes, and all recordings on YouTube. Plus some additional materials. If there are some books or some papers which are relevant to the course, or some movies on YouTube that are relevant to the course, I also list them on this Moodle page. So this is like, an internet site to which you can access with a password given to you. And then you can see these materials. In particular, what is most important, that you can see updated lecture course. Okay. Now, rules of engagement. Yeah, that's a US military term. Okay, so how do you pass the course? Well, for just active participation in registration class. So if you speak once or twice explaining some things, then you get the top grade, which in Poland is denoted as 5, but this is the equivalent of a letter grade A. And if you want to have a super grade, which in Poland is denoted as 5 exclamation mark, it's not 5 factorial, it's not 120. No, I don't know who invented it, but in Poland, instead of having A+, we say 5 exclamation mark. Yeah. So this is given to somebody who actually obtains some new research results. And believe it or not, there was one guy in the first semester who did it in the combinatorics of graphs. He simply worked with me on some issue, and we solved this issue, and yeah, that's a new research result, which is now in our book to be. Okay, and this is the last slide, the last part of the last slide. What are educational goals? Well, let me just read it out. The educational goal for this course is gaining practical knowledge concerning graph system algebras and the K-theory operator algebras, enabling you guys, if you wish, to commence research in this area of mathematics. So depending on the level of involvement, this lecture course might lead to a master thesis or to a PhD dissertation. Okay, so I think that's enough of a general blah, blah, blah. I spent exactly 45 minutes on it. And I think now I can go to concrete mathematics. So, oops, I shouldn't have closed it. I just want to start another file. So I just kill discard changes and open from device. And now the graph book. Okay, let me enlarge it a little bit. Yeah. I think it's good enough. So what I want to do today, that's the part for today. Oops, I have to again choose pen. So that's what we are doing today. I mean, not everything, we just started. But before I will write about it, I would like to recall some basic definitions that you must know in order to understand what I'm talking about. So again, my apologies to all of you who attended this course in the previous semester, but I cannot skip it because then people who are newcomers will not follow what I'm talking about. So I'm going to be as succinct as possible, and I'm not going to write, I'm just going to show things in the book. So first, you must know what I mean by a graph. And that's what I mean by a graph. So I have a quadruple. I have E0, which is the set of vertices. I have E1, which is the set of edges or arrows. And I have one map from E1 to E0, which is called the source map. So to every arrow, it associates its beginning. So if this is my arrow E, then this edge is S of E. And then I have another map, again from E1 to E0, which is the target or the range map. Again, this terminology is used interchangeably. And this assigns to every arrow the end of this arrow. So T of E. So that's what we mean by a graph. And at this level of generality, we have not set theoretical assumptions. I mean, I've never seen anybody studying graphs which would have uncountably many elements, okay? But it's not forbidden by the definitions. In the examples I showed you, yes, everything was countable. Even this projective space, this graph was, of course, infinite, but was countable. And nobody is telling you that the graph need not be non-empty. You can have the empty graph. That's quite all right. E0 and E1 can be empty. But what you have to realize that if your graph is non-empty, then E0 must be non-empty. I mean, you cannot have edges without having vertices, because every edge must have a beginning and an end. Of course, they must be the same. I mean, you might have a loop, You can have S of E equal to T of E. Okay, but every edge, every arrow must have its beginning and its end. So you cannot have a situation in which E0 is empty and E1 is non-empty. But you can have it the other way around. Nobody can stop you from having a graph which is just a collection of points. No arrows whatsoever, just edges. That's quite all right. Okay, so I think now we know what we mean by a graph. And again, this is a question of terminology. If you would like to be very precise, you would always should say directed graph. But since this is the word we are using in every sentence, this would be very awkward to say directed, directed, directed. I mean, every graph we are talking about is directed. So we drop this directed. Our default option is directed graph. And if we want to talk undirected graphs, we say, hey, this is an undirected graph, right? So that's just a question of convenience. I'm actually very sad that the algebraic notion of a quiver, this was what was used by, for instance, Dan Quillen. Yeah, I'm really sorry that this word didn't catch up. This is a very nice word, also in Polish, kołczan. It's a very nice word, and it's much better than a graph. I would like to have a quiver with arrows rather than a graph with edges, but you cannot go against the tide. When you have thousands of publications and books which use this terminology, you cannot change it. It's too late. Okay, but just be aware that when you, in the right context, graph means oriented graph, directed graph, and not undirected one. But we often drop it for the sake of brevity. Okay. Another concept which we desperately need so that you can understand my today's lecture, yes. What is the extended graph? So that's this definition. Yeah, I love this application. I mean, it's so nice. It's so much better than Adobe, where you can just highlight it. It's awkward, it vanishes. I can write, I can point, and it's very also easy to erase. It's called Drawboard PDF. It's free software, which we downloaded just before this lecture. Okay, so we start with an arbitrary graph. And what is the extended graph? Well, before pointing the formulas, let me just say what the idea is. The idea is that we keep vertices as they are, but to every arrow, we associate its ghost, an arrow going in the opposite direction, okay? So formally speaking, we construct the new graph called the extended graph E of a graph E as follows. When you look at the set of vertices, it's the same in the extended graph as in the original graph. Now, when you look at the set of edges, what you take E1, you take like the second copy of E1. So this is the same set, but with now elements marked with stars, okay? But these are identical sets, just different labeling. So you see E1 is defined as the set of all E stars where E runs E1, okay? So this is taking another copy of E1 and taking the disjoint union. And now you have to define, in order to make sense out of it as a graph, you must define the source and the target maps. And as you can guess, whenever you have an edge which is in the original graph E, in the set E1, okay, then the source and the target map are simply the source and target maps that we already had in the initial graph. And here something interesting happens when you take an edge which comes from this ghost image, the mirror copy of an arrow in E1. So when you take E star from E1 star, then the source of E star is defined as the target of E, okay? And the target of E star is defined as the source of E. So graphically speaking, what we are doing, if this is our E, okay, then this is our E star. So source of E is the target of E star, and the target of E is the source of E star, okay? And when you combine it together, you have a so-called extended graph. All right, do you have any questions? By the way, that's a general rule. If you ever have any questions, please don't hesitate to ask. When I'm sharing the screen, I don't see you, right? I don't see your faces. I don't know if you are happy with what I'm saying or not. Never be too shy to ask a question. I think there's a Chinese saying that says that if you ask a question, you are a fool at most once. If you don't ask, you might be a fool for life. I like it. Okay, so that's another thing which I need, some terminology, which is very useful. I will use the concept of a regular vertex. It's very important for the Cauchy-Krieger relations. So I have an arbitrary graph E, and we call it a sink if it emits no edges, right? So the preimage of the source map of this vertex V is the empty set, okay? And analogously, it's called a source if it does not receive any edges, right? So it only emits edges, it's called a source. It only receives edges, so it's called a sink. I think this terminology is quite understandable. And what is very important for us is called regular when, first, it's not a sink, so it emits at least one arrow, but it's not an infinite emitter. So remember when you look, I showed you these Hong-Szymański graphs and Waxman-Soberman graphs and quantum CPN graphs. For the, say, sphere graph, this was a finite graph, so there was no issue with infinite emitters. Nothing was, there was no infinity, right? There were finitely many arrows. So of course, this second condition was satisfied. But and then when you look at the sphere, remember there was a loop at every vertex, so there were no sinks because every vertex was emitting at least its loop. Okay, so every vertex in the sphere graph was a regular vertex. But when you would look at the graph, yeah, maybe I should. Yeah, I keep on forgetting that I can draw. So first I can erase. Yes, I'm just touching and it vanishes. Wow. Do it with all your troubles in life. It would be nice. So what? Let me just draw it, say, in the case of two vertices. Okay, so this is a three-dimensional Waxman-Soberman sphere. By the way, for all of you who know quantum groups, that's exactly the sister algebra of the famous Voronovich quantum SUQ2 group. And you shouldn't be topologically surprised because a three sphere is the topology of a special unitary group of size 2. Okay, SU2 group is topologically, it's a Lie group, which topologically is a three sphere. Okay, and this graph sister algebra is exactly the sister algebra of Voronovich's quantum group. So this is one of these things I was telling about, and this is a non-trivial statement. Is if you want to immediately see on the plate the K theory of quantum SU2, well, you present it as a graph sister algebra for this graph and read off the K groups from Reiban-Szymański theorem. Okay, so you see every vertex here is regular because every vertex emits at least one edge, and there are no infinities. Now, when you look at the ball, so for instance, let's look at this graph. Again, two vertices. So that's the Teplitz algebra of a quantum disk or the two-dimensional ball. And here, well, not all vertices are regular. Well, this vertex is regular because it emits a loop, but this vertex is not regular. So not regular, okay? And then if you look at this quantum complex projective spaces, well, say take again two vertices. So this is if you want CP1 quantum, so it's a quantum 2 sphere. It's the standard Podleś quantum sphere if you know quantum groups. Well, here again you have a problem because one vertex is not regular. So both of them are not regular because one vertex is a sink, it does not emit anything, and another vertex is an infinite emitter. Okay. So these are the graphs which I showed you on the slides, and you can see what regular vertices are. So here, these vertices are regular. This vertex is regular, and here no vertex is regular. Okay, good. I hope it's clear. Let's go on. Yes, now what we need is a concept of a path. Yes, exactly. So this concept. If you remember the hierarchy of concepts, which I drew for you, from graphs, we move to paths. And again, like with dropping the word oriented or directed, so when talking about the directed oriented graph, we just say graph. Typically, when we say a path, we mean a finite path. But we can, of course, have also infinite paths, as you can see over here. But I don't want to talk about it right now. So what is a path? A path in a graph, well, it can be a vertex. If it is a vertex, then we call it a path of length 0. Otherwise, it's a finite tuple, or if you want, a finite sequence of edges, which satisfy the following properties. The end of the first edge is the beginning of second edge. The end of a second edge is the beginning of a third edge, and so on and so forth. So this is pretty intuitive, right? We go from A to B, then we go from B to C, then we go from C to D, and then we can go from D to D again, for instance. Okay, this is a path. Okay, or we can have just, you know, lazy paths, just one dot. It's also a path. Okay, and we extend the source and target maps in the obvious way. So the source of a finite path is the source of its first edge, and the target or the range of a finite path is the range of its last edge. Okay. Good. I think the next thing that I have to explain is just path algebras. So I see there was a lot of combinatorics on the way. Yeah, I'll try to scroll a bit faster. It's nice if you could read that fast. It would be. So you see, I'm sorry, I cannot resist pointing it to you, but that's precisely the combinatorics that we were doing in the first semester, where we could establish. You see, this is a very, very important number, and from what I gather, this is a new theorem that we could count how many paths of length k you can have in a graph which is acyclic and with n edges. So that's a very difficult theorem. And each time somebody proposes to me a shortcut, it's false. And I told you that there was some new result. Yes, so this was a new result by Oscar. That's why he got this A+ for the first semester. That's a combinatorial result. Now I'm scrolling to path algebras. They're almost there. Have some Alexandrov topology on the way. There's actually a lot of combinatorial topology, if you want, on the way. Yes, yes, yes. Yeah, so that's the study of homomorphism of graphs. You remember I was telling you about categories of graphs, so this is where we covered it. So already here, proving that when we really get some push-out diagrams in the category of graphs, that's quite a subject in itself. And I think that a number of these results is new. Yes, graph path algebras, that's it. Okay, so that is what I want to explain to you right now. Well, I'm not going to tell you what algebras are, you should know it. So let's highlight what we're going to talk about. So we start from here. And we go on down there. Yeah, actually, I can end it up here. We don't need to do the proofs. I'm not repeating the course. Let me see if I can just erase part of. Whoops, that was too much. So nice to play with it. No, it actually ends here. All right, so we take E to be a non-empty graph so that we have some non-empty space of paths. Of course, you can also incorporate the empty graph, and then the path algebra of the empty graph is the zero algebra. It has one element, it's a unital algebra, 0 equals to 1. You need such terminal or initial objects when you do some categorical thingies, but so it works, it exists, but it's kind of awkward to do an honest construction when you have an empty set. So let's assume that E is non-empty, which means that E0 is non-empty. And then you take FPE to denote the set of all its finite paths. So this is why I had to explain to you what I mean by a finite path, okay? And now we consider the following vector space. We take simply all finitely supported maps from the space of finite paths in the graph to some ground field, okay? So that's it. As a vector space, that's it. And you immediately see that it's a vector space with the addition and scalar multiplication taken pointwise, okay? That's immediate. This is true for any set X, in particular for the set of all finite paths in a graph E, okay? So now the point is to endow this vector space with a multiplication, right? Because if you want to have an algebra and we only have a vector space, basically all that we have to do, and it's actually written up there, we have to have a nice bilinear mapping from V cross V into V, okay? And this bilinear mapping will give us a multiplication. And of course, you have to prove that it's an associative algebra and so on and so forth. But in terms of additional structure, what you have to provide is just a bilinear mapping on this vector space from V cross V to V. And so basically all that you have to do, you have to take basis elements. And to a pair of basis elements, you have to assign another element in the vector space. And that's why we take the following set of functions. We denote them as chi-p. This is very important notation. This is not something standard. This is what I use, but I think it works. Quite often, people simply skip it. People identify this element in the algebra with a path itself, but this is a bit confusing. So I make this distinction. So basically, for every finite path, I have an element in this vector space Ke, which is defined as follows. Chi p of q, so p is our fixed path and q is any path from this space, FPE, is simply given by the Kronecker delta. So it's just 1 if q is equal to p and 0 otherwise, okay? So this is if you want the support function. That's why I denoted by chi. Yeah, so this is a function on the space which is supported at one point. And I think this is a standard notation for support functions. That's why I chose it. And I dare say that this is a linear basis for this vector space. That's not a difficult observation. I'm not going to argue for this. Such a thing is true for any set. I mean, you can replace FP by any set X and the same would work, okay? So these support functions supported at one point would give you a vector space basis, all right? And now that I have a vector space basis, okay, I can use this vector space basis to define my bilinear map, right? By this formula. That's what I have to give you. I have to tell you how to combine chi p and chi q to something new. Okay, so that's what we are doing right here. And the definition is as follows. Here, everything is automatically well defined because I'm taking basis elements, okay? So I say that the pairing of chi p with chi q is chi pq, where pq is the path obtained by concatenation of p and q, which you can do provided that the end of p is the beginning of q, right? If I have my path p, which ends at the same place where the path q begins, then I can compose them and I have my PQ path, right? But of course, it might happen that the end of P is not the beginning of Q. when I cannot compose them into a path. And when I say that this multiplication is just 0, okay? So this is very, very important. This is the key formula. This is how you multiply in the path algebra. So basis elements are given by paths, and you multiply 2 paths into the composition path, and if you cannot compose, you multiply 2 paths into 0. So that's roughly the idea, which is rigorously written over here. Now we can, of course, prove it. The bilinear map, so this is a proposition which is easy to verify. We're not going to do it. We did it in the previous semester. But you can simply prove that the thus defined bilinear map defines actual algebra structure on the vector space KE. So it's an associative algebra structure, okay? And yeah, so here we check associativity. That's not a big deal. And then we're done. And here we have this. Here you have this formal definition of a path algebra. Okay. Now that we have this proposition proven, this is a formal definition. So we have E to be a non-empty graph, and the above constructed algebra is called the path algebra of E. And if E is the empty set, then the path algebra of the empty set, the empty graph is just 0. Okay. So I think we are basically done with what I wanted to recall. Now I can go into the definitions of today. So I will stop sharing the screen and start sharing the whiteboard. And today's lecture actually begins right now, okay? So I know the proportion is a bit funny because we spent 1 hour and 15 minutes almost on introducing the subject and only 15 minutes on doing some concrete math. But I think it's worthwhile to know where you are driving. So I hope you agree with me. Okay, let's get to work. I want to define for you the relative conpath algebras. And this is taken from this book on Leavitt path algebras, the second reference in the bibliography. But for starters, let me recall what I mean by an ideal generated by a subset. So let R be a ring, and X a subset in R. Then what do I mean by the ideal generated by X in R? So by definition, this is the set of all finite sums. So I have an index I running some finite set F. And I have here, I have elements Xi, which are from the set X. I have elements Ri and Si, which are from the ring R. Okay. So as I said, F is finite, any finite set. And Ri, Si are in the ring, and Xi are in the set X. Okay, of course, for all I in F. That's very important. This is once you have your algebras, especially when you have your algebras presented by generators and relations, then it's very useful and practical to define ideals by some relations which you want to enforce, which you want to have. So you choose an ideal in your R so that you can study the quotient ring, R mod the ideal. And this is precisely what we are going to do. So now here is this key definition of today. We have the soup of the day. This is the definition of the day. So what are the ingredients of our soup of the day? Well, first we have a graph, any graph. So let E be a graph. Let K be a field. and X be a subset, any subset of the set of all regular vertices in my graph E. So you see what I recalled for you are exactly the ingredients that I needed to make sense out of this phrase, okay? Now, the relative con algebra which we denote as CKX of E. The relative con algebra CKX of E of the graph E is the path algebra, which I also defined for you, of the extended graph. It's a path algebra K bar of the extended graph, which I also defined for you, graph E bar, divided by the ideal generated by the union of the following subsets. Okay, now let me go to new page. So the first subset is the following. It's chi E star times chi F minus the Kroneker's delta E comma F times chi T of E. And we take all such phrases. So EF is an arbitrary edge. So we do it for all pairs of edges, okay? So, well, maybe let me do it like this. Let me denote it, denote it as X1. How about this? Okay, so X1 is by definition this set, and X2 is by definition another set. Now, what you take here, your running argument is a vertex. So you go over all vertices, but where? In X. That's the trick, okay? This is this theory of relativity, if you want. We are relative to the subset X. Okay, and what we do the following. We take the following expressions. We have the sum. This was ugly. Sorry, my handwriting is far from beautiful. Sum over all edges emitted at V. And you see, it makes sense because V is a regular vertex, okay? So this set is neither empty nor infinite. So the sum makes perfect sense. And now we take chi E times chi E star, okay, minus chi V. All right. So here you have first sanity checks that you don't get something very trivial. So now maybe let me finish. Now the X is simply given as the union of these two sets. Okay. So if you want the formula, I write CKX of E. That's by definition, I take the path algebra of the extended graph and divide it by the ideal generated by the set X, okay? So this is the relative con path algebra. This is your take-home message for today, all right? But now let me do a sanity check that this definition holds water. So of course, when E is different from F, that's not very interesting. We just want elements in my quotient algebra. I want elements which look like this: chi E star, chi F. I want them dead. I want them to be equal to 0. Okay. So, but look what happens when E is equal to F. Okay, then this is our E, and this is our E star. All right. So you see, I'm having first E star, and then I'm having E. So I go by E star, but the end of E star is the beginning of E. So actually, chi E star, chi E multiplied to something non-zero in the path algebra, right? In the path algebra, this is chi E star E. Okay, that's composable. Going first by E star, then by E makes sense. Okay. But now what I want to have, and I don't have it in the path algebra, I want this to be equal. I want to make it equal. So when I take the class chi E star E, I want to make it equal to chi of the end projection of E. Okay. So this is why this is the equality which is enforced by taking the set x1. Okay. Now let's do the sanity check in the second case. Now, if you go first here, you first go by E, and then you go by E star. Again, it makes sense. So I can write that chi E, E star, that's some non-zero element in my path algebra. Okay. But here, what is important, I don't want to make it equal. In general, I don't want to make it equal to chi of the source of E, right? That's not how it works. But I want to sum all these guys. Okay. So let me erase this quality. Yeah, inequality, and okay, I also erase these braces, and I'll modify it. So now I have this sum over E in S inverse of V, okay? And that sum is supposed to be equal to chi of S of E, which is of course chi of V, okay? So that's the second relation I'm enforcing. So when you look at arrows that arrive at a certain vertex, you don't care. This is just about edges, right? You know that an edge times edge star, that edge star times an edge is just this final projection here. But when you're looking at edges emitted from a vertex, you have to take into account all of them. Okay. So that's these. This is so-called Kunz-Krieger relation number 1, and this is Kunz-Krieger relation number 2. So these are these famous Kunz-Krieger relations I promised to you in the syllabus. Okay. So Kunz-Krieger relations. Okay. And now, why do we make it relative? Why do we make all this fuss with this set X? Well, because it's very convenient. This is like a homotopy. We make the homotopy between the absolute Kohn path algebra and Leavitt path algebra. And let me now continue with the definition. We still have 6 minutes. So when we take, let me write it like this: the relative Kohn path algebra C empty set KE, which we denote simply as CKE, that's just the notation. So that's the absolute, the Kohn path algebra. So this is called, simply the Kohn, without the relative, the Kohn path algebra. Okay. And the relative conpath algebra CK, and here just take all regular vertices of E. And this you denote as LK of E. And this is called, well, it's called the conpath algebra of E. This is called the Leavitt path algebra of E. So you see, by regulating this set X, which can vary from empty set to the full set of all regular vertices, we can either have an algebra which have few relations. So only first conscriptor relations are implemented. The second conscriptor relations do not hold. And that's the conpath algebra. It also has its sister algebraic counterpart, which is called the Teplitz algebra of the graph. So when you take the universal completion of the absolute conpath algebra, then you get the Teplitz algebra, which is a sister algebra. And then when we enforce both conscriptor relations, the type 1 relations and type 2 relations, and take this full quotient, then what we obtain in the quotient is this Leavitt path algebra, and now graph sister algebra is the universal enveloping sister algebra of the Leavitt path algebra. So at least these basic ingredients have been defined for you. We have only 3 minutes left, so I only want to end by listing some elementary facts. Only 2 of them. So first, note that the Leavitt path algebra we can view, okay, we can view as the absolute conpath algebra divided by the ideal generated by X2. Right, remember? So that's X2, that's this set, a set of conscriptor relations for the second type, and with an X being equal to all regular vertices. Sorry, yeah.
Sorry to interrupt you.
Yeah, sure.
You're overloading X there. X was a subset of regular vertices.
Yes, I should take all of them.
And then you say X is the union of X1 and
Yes.
X2. And
Yeah. Yeah. So here I meant X2, but this is wrong because X2 depends on I'm so sorry. Thank you, Niklas. Oh, you're absolutely right. Darn. Okay. So yes, you're absolutely right. Thank you so much. This is what happens when you don't follow the notes and just improvise. Yeah, thank you so much. This is very important. So this is, let's call it Y. How about Y? Why not? Yeah. Okay, and then this is, yes. So Y depends on X, okay? So this is also Y. But now when I define Y2 and you know how it depends on X, maybe here I can say Y1 of X, Y2 of X, and Y of X, okay? So that's more precise, okay? And now here I can make sense out of it by simply writing Y2 of X. Sorry, not of X. Yes, Y2 of regular vertices, all regular vertices in E. Okay. So that's the first elementary fact. And since I have an appointment, I have to end sharply right now, 3:45. We will begin with a second elementary fact next week. And we have now a half-an-hour break, and we'll resume 4:15. And let me stop recording and see you then. Stop recording.